Alrighty, welcome back from your break. Time to continue on with chapter 19. We're going to move from interference into diffraction, and this is the second part of how we treat light as a wave. It's a phenomenon kind of that actually allows you to have interference, but you can talk about interference without understanding why the two waves are spreading out as they are. So here we go, diffraction. When a wave interacts with a barrier that's roughly the same size as the wavelength of the wave, diffraction will occur. So this only occurs when the wave is passing through a hole that's comparable in size of its own wavelength. So if it's an ocean wave, for example, the wavelength might be a meter or a couple of meters, then you'll only see it spread out like this when it passes through a hole that's roughly that size. So when you do have an ocean or a water wave passing through a small, narrow slit, it will kind of spread out in these ring-like patterns like this. And it's not going to be perfect all the way around like this, with water. But you will see a spreading out. It will spread out like this. Whereas if you have a giant barrier that's really big compared to the size of the wavelength, the waves in the middle here, they just keep going straight through. They don't really notice that there's a barrier. And it kind of makes sense of this because the water molecules here, they don't know that there's a barrier way over here. The only way they can get that information is if it's transmitted. But if it's really far away, that information is not going to be transmitted well, and therefore they won't really feel the effect, and so they'll just keep going in a straight line. Now, the particles that pass by that corner, they're going to curl a bit, and you can see in this picture they curl a little bit. But it's just a little bit here and just a little bit here, and that's not really propagated throughout the entire thing. Whereas if all the water passing through had been near that opening, then all of it would have felt that effect, so to speak. So that's diffraction. It's the bending of a wave as it travels through an opening or travels past a barrier that's in comparable size to its own wavelength. So you can imagine that for light, which has a very small wavelength, it's only going to diffract when it passes near some objects that are very, very small or very, very thin. Okay, so now we're going to look at a new type. Instead of just the general concept of diffraction, we're going to look at a specific diffraction through a single slit. And this is very similar to the video we saw where the guy held the hair in front of the laser light. There's a single slit, that's the obstacle there. In this case, it's typically a single opening and the light is passing through and the light is then diffracting. And the way that we can kind of analyze this is by examining the slit here. So this whole thing is the opening. By pairing up particles, so like we could take this particle here and this particle here and treat them as an interfering pair. And then you could take this particle here and this one here. And so you can make these guys in pairs. And so each of them that are a pair are going to be a distance, the width over 2 apart. So we're going to call the width, the distance between these, or the width of this slit is W. So the two interacting light waves, if you will, the sources of the light waves, are half the width apart. And then this distance that we want them to be offset, if we're looking for a minimum here, then the distance that they should be offset right here is, say, a half a wavelength, or 3/2 of a wavelength, or 5/2, etc. Some number of half wavelengths apart would tell us where that minimum is going to occur. And the rest of the analysis, the approximation that tangent theta and sine theta are the same because the angles are very close to each other. All those other approximations that we made for double slit interference are exactly the same, except for the distance here we pick up a factor of W over 2, and then therefore for the wavelength we also pick up a factor of 2 in the denominator. Those two factors of 2 essentially cancel out, leaving us with a formula that's more or less the same as the formula for the bright spots for a double slit interference. So it can be a little tricky to remember, but for single slit interference, this formula is giving you the dark spots, and for double slit interference, it was the formula giving you the bright spots. So again, these variables are all the same as they were. This, instead of the D right here for the distance between two slits, we have W for the slit width for a single slit, etc. Wavelength, distance to the screen, and then any integer you put here. So right here is going to be the first one, right here is going to be the second one, then right here is going to be the third one, etc. And these are spaced out like this. But typically, what you're actually going to measure in an experiment, and then what's going to be given to you in problems, is the width of the central bright spot. So from here down to here. So this total distance right here is typically what's asked or what's given in a problem. And so you can remember that this is a dark spot and this is the center. So the distance up to here is the first dark spot, the distance to the first dark spot, and then you can double it to get the width of the bright spot. So the width of the bright spot is twice the distance to the first dark spot. So that's very useful for calculating some problems. All right, and here's an example. Suppose yellow light with a wavelength 589 nanometers passes through an 0.11 millimeter slit and hits a central bright spot 2.6 centimeters wide. How far away is the screen? So, as I said before, we'll just draw a little sketch so we can label all of our stuff. So we're trying to find the length away to the screen. The central bright spot, is 2.6. That's the total. So by drawing this little sketch, you can see right away that this has to be 1.3 centimeters. That's our x in our formula. We've got this little slit here, W. Okay, and so we can set up our formula. X equals m lambda L over W. And m right here, since it's the first bright spot here, we have that m equals 1. And so we can solve for L and we can get L equals, multiply W up here, xW divided, m is 1, so divide by lambda. Then we can plug in our numbers. X is, not 2.6. X is 1.3 centimeters. W, the width of the slit, is 0.11 millimeters. So 0.11 millimeters. Maybe I'll go like this so it's clear. And the wavelength here is 589 nanometers. So how far away is the screen? L equals. So we're going to have to do some unit conversions here. Remember that centimeters is 100th of a meter, so 1.3 divided by 100 times 0.11 divided by 1,000. Then we're going to divide by 589 times 10 to the negative 9th for nanometers. And I've gotten out 2.43 as my distance to the screen, 2.43 meters. So if you convert centimeters, millimeters, and nanometers, you can do it just as you're typing in your calculator, add on the suffix 10 to the negative 2nd, 10 to the negative 3rd, and 10 to the negative 9th. You should get 2.43 meters, and that makes sense given this is a couple of centimeters, this is 0.1 millimeters, that the length is about 2.5 meters. That's a very reasonable answer given all the other problems that we've been looking at, or that you will see when you do the problems. Okay, just a couple topics left. Next up is diffraction gratings. So if you can get a pattern like this from just one single slit or a pair of slits, you can imagine how much nicer and cleaner the pattern is going to be if you have hundreds and hundreds and hundreds of slits, maybe even thousands of slits, all next to each other and all equally spaced. So the reason that's valuable is you get interference. Instead of just two things interfering, you've got hundreds and hundreds of things that are all interfering, and if they're all spaced nice and evenly, then the pattern you get will be very refined and exact. It won't be like this big stretched out blurry bright spots. They'll be very distinct spots. And so it's kind of cool. This is a picture actually. There's a laser being shown in this way. This right here is a diffraction grating that the laser is going through, and then it's spreading out along these different paths. And so you can see the green one, the distance that the green one goes is actually a little bit less than the distance that the red one goes. So the distance the green is spreading out is not as much as the distance the red is going, and that's because green and red have different wavelengths. And so you can know that the lambda, the wavelength symbol, it's in the equation, and so if you change the wavelength, you're going to have a different distance that these light dots are showing up. So the math and setup is exactly the same as for double slit interference. The only difference is these dots will continue on farther and farther and farther away. They won't only be in the middle. And so with double slit interference, because they fade out as you go farther away, we use the approximation that the distance between the dots is small compared to the distance to the screen. With diffraction gratings, these dots can spread out really, really far. I mean, you're talking 45 degrees, even larger angles. And so the approximation that the angle is small is no longer valid. So we can't substitute out sine theta, right? Remember we had something like this, and we had like an x here and an L here. We can't substitute that sine theta is approximately x over L because it's no longer true. I mean, if you just look at something like this, if here's x, here's L, here's the hypotenuse, and here's theta, sine theta is x over h, which is no longer approximately x over L because h and L are now different lengths. So that's not really any trouble. We can just leave the formula in terms of m lambda. M is any integer again. The center one is 0, etc., etc. Then the first one, second one, third one, out as you go. You just leave in sine theta. So when you're solving a problem with diffraction gratings, you actually need to use sine or sine inverse once you know the angle or once you find the angle, instead of just using this ratio x over L. But you can still find x and you can still find L. You just have to kind of combine this with the fact that sine theta equals x over h, and then tan theta equals x over L. And so you can relate theta to x and L and h in any combination that you need to by being careful with your trigonometry. All right, let's do an example of a diffraction grating problem. So suppose blue light with wavelength 434 nanometers is shown on a diffraction grating at a screen 1.5 meters away. The spacing of the dots is 0.55. I got this problem out of the book actually, and I think this is kind of poor of them to say the spacing of the dots is 0.55 meters. The spacing will change as you go farther away. The spacing will get larger, and so I guess we're going to assume that's the center spacing. So here's our diffraction grating with lots of little spaces, and then here's the spacing of the dots. Let's assume it's to the first one. So this is m equals 1, and this is m equals 0. So the center bright spot and then the first dot is 0.55 meters. The screen is 1.05 meters. This is our L. Over here we have the distance between all the little dots, d, and then we have the wavelength, lambda, right there. Okay, so we can say that lambda equals d sine theta. So we need to figure out what this angle is in order to find d. Okay, so we can do tan theta equals 0.55 over 1.05, and then we can get theta. Let's do that real quick in the calculator. 0.55 divided by 1.05, and then take second tangent, and I get 27.6 degrees. 27.6 degrees. And so now I can plug that in over here. So let's say distance equals lambda divided by sine theta. Well, my lambda is 434 nanometers, and I'm going to put in here sine of 27.6. So the distance between my spacing here, I'm going to take sine of that angle, and I get 935 nanometers, which is almost 1 micrometer. 1,000 nanometers would have been 1 micrometer. So the distance of our spacing. Notice that the distance between these is very, very small. And again, it has to be because we said that diffraction is only going to occur if the holes or the spacing is comparable to the wavelength of light. So it has to be somewhat close This is off by a little over a factor of 2, but it has to be somewhat close to the spacing of the light. Otherwise, the light will just pass right through and not exhibit this diffraction properties. Okay, so we've learned about 3 different types of diffraction or interference. One is single slit, one is double slit, and then one is a diffraction grating which has hundreds and maybe thousands of slits. So I just want to visually show you the difference between the interference patterns that develop, and kind of in your head you can kind of be visualizing these. So with double slit interference, you have a central bright spot. In fact, all of them have a central bright spot. But with double slit interference, it's brightest in the middle, and then as you go further away, it gets dimmer and dimmer and dimmer, but the spacing stays the same. So you've got dim spots at the half integers, and you've got bright spots at the integers. And then for a single slit, because the bright spot in the middle is twice as wide, it throws things off a little bit. Now you have dark spots at the integers. So here, these are the dark spots. That's our formula, is finding these, right? These are the dark spots. And then the central bright spot is twice the distance between the first dark spot and the center. So a diffraction grating, it's very similar to a double slit experiment, except instead of being kind of broad, bright, blurry spots, the bright spots are very concentrated exactly into the one spot where they are, instead of kind of extending in a larger variety. And the reason is because you have so many diffraction grating lines overlapping that it really kind of eliminates any of the blur or the spreading out of the wave and just isolates it right where it is. And so this is all destructive interference everywhere except at that perfect little pinpoint spot where it occurs. So the location of the diffraction gratings in the double slits are very comparable. They're always bright spots, it's just the diffraction grating has a lot more refined values. And also you can see like the amplitude here is a lot higher even when you go out to m equals 3 or m equals 4. And so the angle that you see diffraction grating light still showing up is a much larger angle, and so the small angle approximation was no longer valid, so we have to use d sine theta. Now for double slit interference, this book here has put d sine theta, but of course in this I got off mcatreview.org. This one here, it includes the full equation, but in ours we replaced sine theta with x over L, so we had dx over L equals m lambda, and then I think I rearranged it to solve for x. So x was equal to m lambda L over d. That was the equation that I had presented, but you can see it's the same thing under the small angle approximation. And then single slit is kind of the oddball out because the equation there is very similar, but you're finding the dark spots instead of finding the bright spots. So I hope this slide has kind of refresh your memory on the 3 different ones and shown the difference between them. The only other thing we learned really in terms of interference and diffraction is for thin film interference, and that's the one where you have to worry about when the light is bouncing off of something with 2 surfaces, the 2 outgoing light rays, they might interfere constructively or destructively depending on whether the light inverted and how long the thickness was compared to the wavelengths. Okay, the last topic in our book I'm not going to talk about at all. It's kind of complex and difficult to explain, so I want you to read pages 530 and 531. It's about a page and a half in your textbook. I'm not going to be asking any problems about it, but I encourage you just to look at it for your own benefit and curiosity. It's about how you can determine whether there's 1 light source or 2 light sources. So, like for example, say you're looking at a car driving at you on the freeway. When it's really far away, it looks like just a single bright light. But as it gets closer to you, you can then discern that there's 2 separate different light sources. And so it talks about the criteria in how we can determine with our human eye or with telescopes for looking at stars and stuff, how you can determine whether there's 1 light source or multiple light sources that are very close together. Because when the light is coming into your eye or your telescope, you get diffraction, and it makes it more difficult to tell which is which. Okay, so congratulations, you made it to the end of chapter 19, which is actually the end of this entire unit on waves, which included sound waves and then lots and lots about light waves and optics. So we'll have a test coming up in a couple of weeks probably, and then our next unit is going to be electricity. So I look forward to talking about all this stuff in class.